Okay, so that's mirrors. Let's do lenses. Now,
the reflection law is always true.
I'm sorry?
Black holes. The law of reflection.
Sure it is. It's just the light's not reflecting off the black hole. If it did reflect, it would follow the law of reflection. Yeah, good try. All right, now, to simplify life, we're only going to do biconvex and biconcave lenses. And by the way, you may hear me call them double convex as well. Same. We haven't? Okay. Thank you. Good catch. There's different types of lenses. There's where it bulges out on both sides. The bulging out part is what we call what? Convex. And so if it does it on both sides, we call that biconvex or double convex. We might also have two bulging in which case we would call that biconcave. And these are the two we're going to principally deal with. Others that I at least want you to know what they're called are that, which is what? On one side it's flat, and what do we call a flat surface? Plane. And on the other side it's convex, so we call this plano-convex. Yeah, very good. Actually, no. Contact is a combination of both, and depending on what kind of vision you have, it can be, well, we're not going to get into the terms, but it has either a negative or positive, what's the term? Meniscus, I think is what
Is that what the negative thing, is that what the little number on the wrapper means? The negative?
Yeah. And then what else might we have? Good, plano concave. Right, where it's plane on one side. So those are the four I want you to know what they're called. Know that you can have any combination thereof, and the one that has the greater curvature is going to determine what happens to the light. And we'll talk about that in a second. All right. So, speaking of, let's look at a double convex lens so we can describe its light's behavior through it. I have a light ray coming in. When it hits this lens, which is made of glass usually, right? What's going to happen to the speed of light in glass? It's going to slow down. So how is this ray going to bend? Up or down?
Wait, so is this like a big piece of glass, or is this like a piece of glass with a hollow part?
No, it's solid in the middle.
Would that change things if it was hollow in the middle?
Yes, slightly, yeah. But then when it gets to the other side, which direction is it going to bend?
More downward.
Ah, good. More downward, because which wheel hits first? Think of the remote control car.
The left.
Left wheel hits, and when it hits it, speeds up.
Right.
And so it bends down even more. Yeah, I got you with the voice trick. Good. What about this ray? Same thing, only
Less.
a little less.
Not less.
Because the angle that it hit, right, if we zoom in, let's zoom in, see how when the left or the right wheel hits first, it's a long time before the left wheel hits. Whereas right here, it's not as long before the left wheel catches up.
How about it?
Very good. So, what about a ray that comes in and hits square on in the center of the lens? Straight through, right? That's like when you go straight from the carpet to the tile, or from the tile to the carpet. You don't bend, even though you change speed, because both wheels hit at the same time, right? If both sides of the wavefront hit the barrier at the same time, it's not going to bend. And that's going to be important later. What about this one down here?
Did I bend up?
Up? Why on earth would it bend up? Everybody else is bending down. Yeah, because it's cool like that. The left, because of the curvature, now the left wheel hits first, and it slows down, causing it to bend up slightly. And then when it hits the air, bends up again, and you see the pattern forming, don't you? So, a convex lens is what kind of lens?
This kind of lens. I don't know. No, this
Converging. It causes the light to converge. Has anybody ever converged light with a convex lens? Yeah, magnifying glass. When did you converge light with a magnifying glass? Exactly, when there's an ant right there, right? Always draw your ant anatomically correct, like all 6 legs on the thorax. Right, and so, right, and smoke, right?
Is that how like lasers work? How they're like a focus point?
Partly, yes. Now, of course not. You're much more humane than that. What about biconcave? What's going to happen to that ray?
Wait.
Why?
It depends where the image is.
Nope, doesn't. If that ray comes in and the left wheel hits the glass first, that wheel...
The left wheel hits it first, and that slows down so it's going to turn around.
Exactly. Well, turns to its left, or up from our frame of reference.
Wait, it turns up?
Yes, because here's the remote control car. This wheel hits first now, and it slows down. So this wheel goes faster, bending it that direction. But then when it gets on the other side, it's clearly going to bend more up because the right wheel hits first and speeds up. Thank you. Oh wait, got one in here that's not us. Sorry.
You got 2 though, right?
Yeah. Thanks. Now, what about this one?
Not as bending.
Good. It's going to bend in the same direction, but not as much. Do something like that. And then if it goes straight through the middle, it's going to not bend at all. Then down here, because of the symmetry of the lens, now that we're on this side, it does the exact opposite, bends down, but not very much. causing that light to spread out. So double concave lenses are diverging. Now,
Switch from their original.
yeah, they're the opposite of mirrors, right? Now, what do we call where the ant is? The focal point, because by definition, focal point is where light rays either come together, intersect, converge, or where the parallel lines appear to have originated from. So what do we do down here on this concave lens?
We bring the normal back.
Yeah, we project these back,
No, what they call? What do they call?
the rays. If I project those rays back, then guess what they do? Yeah, they converge. They appear to be coming from the same point, which we call the focal point.
Now, if you're normally don't line up exactly.
Yeah, it's just because we didn't draw the lens very well.
In order to find it, you only really need to draw one arrow's line down, right? Because then you like the center.
Yeah. Yeah. Yep. Yeah, actually, a telescope uses a combination of convex and concave. My favorite example is like a peephole, because this serves the same purpose as a convex mirror. It allows me to see a wider range of vision by making the object smaller. Well, when I'm close to the focal point, right, within the focal point.
So that is upright and reduced.
Careful. We're going to draw the ray diagram to see. Remember, I don't want you to try and memorize rules. I want you to be able to draw ray diagrams because it's a lot easier. So that's an introduction to the types of lenses. Now we can learn how to draw ray diagrams with them. And guess what we have?
Biconvex.
Yes, we have a biconvex lens, and in order to locate the image, guess what we're going to use?
Oh, and
Yes, our same rules. Parallel in for the first principal ray, parallel out for the second principal ray, and then center. Now, do you remember my disclaimer, my parenthetical warning about center on mirrors? I said center is going to be a little bit different for lenses than mirrors. On mirrors, center meant what? Yeah, twice the focal point, the center of curvature. In lenses, center means the actual center of the lens. But that's the only difference. You use the same three rules for every kind of mirror and lens. The only difference is when you're dealing with mirrors, center means the center of curvature. When you're dealing with lenses, center means the actual center of the lens itself. Let me show you. Okay? Yes?
we did like this with light coming from the top and light coming from the bottom, but about light coming in from the side.
They all behave the same way, but they're harder to draw. And since we're interested in locating the image, we want to take the simplest rays.
Okay.
But yeah, every other ray that forms the image follows the same behavior. Yeah, same pattern. All right. Now, biconvex lens has how many focal points?
One.
Oops.
On the outside.
Look at this. Is there... let me back up. How many centers does it have?
One. Two.
Yeah.
One circle.
There's one center. That's the center of this circle. And then this side has a center. That's the center of that circle. So it also has how many focal points?
Two.
2.
Where's the second?
If the light's coming in from the left, it's going to converge at a focal point on the right. If the light's coming in parallel from the right, it's going to converge on the focal point to the left. So when I get ready to draw my biconvex lens here, I need to draw both focal points. And I want to make sure they're equidistant from the lens. So you can call them F and F prime, or you can call them F1 and F2, or FL and FR, I don't care. But just know that they're the same distance from the lens, they're just on opposite sides of the lens. So let's draw our object, and then we can begin. What's the first ray going to be? Parallel N. And what on earth is going to happen to that parallel ray coming in? Good. F or F prime? Which focal point? F prime, because we're dealing with a convex lens. Because it's a lens, it's going to pass through the lens, and because it's convex, it's going to converge. So it goes down.
Now, how do you know that it's not on the up part? Like it's not. Like what if the image is a different height? You understand what I'm saying?
If I had a different height image, I would just start the ray in a different place, and when it hit the lens, it would still go through the focal point.
But I mean, like, if you go on the top, they all go down to the focal point. It's the focal point.
All parallel lines in go through the focal point. That's why we use parallel lines. You'll not. No, I'll give you the focal point. Yeah.
It doesn't necessarily have to be right when you put it, right?
Right. Except for like in the lab you're going to do, you're going to know the focal point and have to predict where the image is going to be, so you need to measure it. But for a sketch like this, no, it can be anything. Right. So that's parallel in. What about parallel out?
The center.
Well, first of all, ray 2.
In the center. No,
What? Which one?
The one that's good on the
F prime.
I go through F. Now why? Because when it hits the lens, it's going to go what? It's going to go parallel out. Right? And again, think of the trucker's maxim.
Oh, yeah.
If it came from right to left, parallel, what would it do? It would go through the focal point on the left. So I can do that backwards. I can go through the focal point on the left, and that will put me parallel out.
Now, we went under the axis, so what does that mean?
I'm just following the rules. I'm going through the focal point until I hit the lens, and then going parallel. You'll see what it means in a second. But right now, I don't care. I'm just drawing the principal rays to see where they lead me. Okay? What's the third principal ray? Center. And remember, it's different than centers for mirrors. And that's why, did you notice I didn't draw the centers of curvature on my picture? Because I don't want it to confuse me. I'm going to draw them on mirrors, but I'm not going to draw them on lenses. Because for lenses, center means center of the lens. And I kind of missed it, but it's right there, right? Where the principal axis meets the lens.
If you go through the center, just go through straight.
Right, and if I go through the center, I don't bend. And so I just go straight through. Do those three principal rays intersect?
Yes, it is.
Yes, they do. That's the tip of the arrow.
Really smaller and then the butt's always at the base.
Exactly. The butt's always on the principal axis. It's always at that center line. And so that means this image is inverted, reduced.
Actual, because there's actual
Okay, the options are real or virtual.
Real. This on both sides this time.
Does the light actually pass through the point where the image is?
Yes.
Yes.
Real.
And so it's real. And I can check that by asking myself, hey self, do we have solid lines or dotted lines? Solid lines. Remember, solid lines tell me where the actual light ray goes. Dotted lines are where my brain thinks the light ray came from.
What about,
There's not hard, fast rules that lenses are always real and mirrors are always virtual or vice versa. It depends on the type of lens or mirror, and it depends on where the object is. And again, I could have you memorize rules, but I'd rather you learn how to draw ray diagrams. Yes?
So is that line, that's not the ground?
Not necessarily, no.
Because if it was the ground, then that image would not be real, because there's no light on the ground.
But then you don't have half a lens. Huh?
Yeah.
What happens if
Okay.
you put the arrow not at the center? Like if you raise it? Like if it wasn't touching the bottom of the glass?
Oh. Yeah, no. But what it would mean, if it was like this,
Yeah.
It would be that same place.
what it would mean is I could do the same rules for the base of the arrow, and they would end up right there. But it just saves me time by making it all the way down. All right? Yes, please.